Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and you have entered my virtual classroom because you're here to learn a thing or two about math. That's great. Thank you. It's an honor and a privilege to be serving you today. Come on, step inside. I got something to show you today. It is a Q&A video based on setting up word problems and solving literal equations. I have 6 questions that are presented for us here today, and you can take a look at them right here. Pause the screen if you feel like it, because I'm going to shift off this in a bit. What these videos are, basically, my students ask me some questions in class, they write them down, I go and look to answer them. I try and do once a week, unless, once every 2 weeks, I think. I haven't done one for a couple weeks now. And I respond to them because they enrich their lives in some way or another. At least I sure hope so. So it's something that I'm planning on doing with them. I have 6 questions for them. Now, how do they get a question on here? How could you get a question on here? Well, it's really quite simple. The students are the ones who do ask the questions, and what they have is a nice little assignment sheet here, a cover sheet for all their stuff, and they ask their questions down here. At the end of 2 weeks, I collect them. I try and find some questions that I feel are best to serve the whole community in some interesting ways, something that's very broad and general, and I can cover it with a nice large brush. I go up to 10 questions. Here I only have 6. I think last time I had 5 or 6 as well. They have to relate to the topics in the last couple weeks that we had. In this case, setting up word problems and solving literal equations. Solving literal equations were among them. And once I get the live chat stuff up, I'm going to be starting to allow that as well, live chat section. Once I start doing live streams for these videos, I don't know when it's going to start. I've tried to do some things with it, and I'm still running into some technical difficulties. Oh well, it's the nature of the beast right now, so figure it out. But for now, watch the archives. I think you'll be good. Without further ado, let's go ahead and get started. And the first question that I'm going to be answering for what's being asked is, how can one easily create and define variables for a word problem? So what's being asked here really is, if you have a word problem of sorts, what do you do with trying to solve, I always ask my students to create a variable to define their variables along the way, so when they create equations, those letters mean something. When they solve for it, it actually has purpose. And it's not just for me. It is a little bit. It's for the person that's reading the equation saying, where did this come from? What's this? But it's also for them. When they solve this thing, I want them to have a good look and idea of it and say well, how does this pertain? Does my equation even make sense? And let me start by stating here that in my particular classes, I gave them word problems without actually having the question there. The main reason is because we weren't actually solving them. See, they were systems of equations kinds of word problems, but we haven't been solving systems of equations yet. It was more along the vein of, I guess just can they do it? Can they set something up? Get the expressions in the way? Because we did the same things with inequalities, but very basic ones, and some basic equations. But I didn't give them the question. I gave them the situation. But based on the situation, and based on the units used, and based on what we didn't know yet, how would they set up a variable? Now, obviously, if you have the question, it's going to be a lot easier, so I can answer this in 2 distinct ways. But what I'm going to do here is I'm going to show you 2 different actual examples here. First example will be this one. It has something to do with hot dogs and sodas and how much they charge. And then the question becomes, when they give you information, how many hot dogs were sold and how many sodas were sold. The other question that I'm going to place to the right of it right here is, you and a friend go to a hot dog stand, blah, 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 and hot dogs and sodas are sold, and the total amounts of what were sold here with the total amounts of hot dogs and sodas that you purchased. And the question is, how much do they cost? So if you can kind of see the difference between those 2 questions there, they are 2 different questions being asked. And so the first thing that I'd recommend for someone who's trying to define variables, for my own students, I'd say is this. Listen to your teacher, because your teacher talks about the fact that when you define variables, you can't just identify what the letter stands for. And what I mean by that is, if they define things, let's say we used H to represent hot dogs and S to represent sodas, and I don't love S because it can look like a 5. But if I say H equals hot dogs and S equals sodas, this is kind of a problem. I want you to keep this in mind. This word problem involves hot dogs and sodas. This word problem involves hot dogs and sodas. So what if I did the same thing here? Whoops. What if I said H equals hot dogs and S equals sodas? I want you to think about the actual concern with this is. What if we get answer? And remember, I'm not solving these. I'm not solving it in the video. I'm not solving them in my class. But imagine that you solved these. Imagine that I got a solution here that was H equals 7 and S equals 4. And let's say over here, I got some answers here that said H equals 1 and S equals 3. I don't care. Word problems need context. The answers need some sort of context with it. Units. I'm not going to stop here and say, well, I'm done. I want to answer the question. The question was, how much do hot dogs cost? How much do sodas cost? Okay, because of the question, I guess that means H equals $1 or 1 cent or one $5 bill. I don't know what the units are. I guess it's supposed to be in money. But when I define these things, I didn't represent them as these are dollar amounts, I think, that I'm looking for. I think you could do cent amounts, depending on how you set up the equation. And I'll set up the equation so briefly that it's just going to be a thing. But for this one, it was how many were sold. And some people forget to go back and look at the actual question and say, what am I answering here? Because I promise you, when people just write H's hot dogs and S's sodas, they think 7 hot dogs, 4 sodas. In this case, that would have been it. The other one, 1 hot dog, 3 sodas. No, we're not trying to get the amount. There, we're trying to get the cost. So you can see that there's an issue. So listen to the teacher when he says, make sure that when you define variables, you identify which specific characteristic you are referring to. H doesn't equal hot dogs. Hot dogs is not a number. H can equal the number of hot dogs sold, and S can equal the number of sodas sold. That's fine. So this time, when I get an answer like H equals 7 and S equals 4, I know what they mean. 7 equals number of hot dogs sold. There were 7 hot dogs sold. On this one, it's not going to be number of hot dogs because that's not the question. We know that information. How many hot dogs were purchased? 3 plus, there's something else, plus 4. 7, I guess 7 there. 3 plus 4 equals 7 hot dogs were sold. That's not what we're trying to figure out. Plus, they're in different spots for different reasons. We're trying to figure out how much they cost. Here, H is cost of each hot dog. Cost of each hot dog. And furthermore, this has a unit that we need. And in some cases, you're going to be doing it in dollars. I'll put this in dollars in this time. S would equal cost of each soda. And that's also in dollars. So now that time, why is this important? Number 1 is for the answer. But number 2, to set up your equations. When you set up an equation, it's so important that you know what units you have to indicate what values you kind of have been working with. And these aren't the best word problems to get the most diverse equations. I understand that. But you got to know what it is you're looking for and how you can use it to multiply with a coefficient. It's all about unit conversion. Sadly, I'm not going to dive too deep into that. But this is really how you create and define variables. How do you create variables? Look for what you don't know. You got to look for what you don't know. In the first problem, we know how much each hot dog and soda costs. We don't know how many there are. In the second one, we know how many hot dogs and sodas there are. We don't know how much they cost. So you see that difference there? So that's number 1. Figure out what you don't know and what you need to know. Clearly, we don't need to know the weight of the hot dogs. We don't need to know the length of them or anything like that. Those aren't the characteristics we need. The second part of it is how do you know how to define them properly? Include the characteristic you're looking for. They're all within the same question. The answer is the same for both of them. You're looking for what you don't know, and you include that characteristic in it. All right. That way, when I create equations, because I'm overrunning question 1 already, the other questions, I promise some will be faster here. Each hot dog costs $1.50. So if I represent these in terms of dollars, I could say $1.50 per hot dog. times the number of hot dogs, and this gives me a term that represents the total amount that I made by selling hot dogs here. Plus $0.50 per soda times the number of sodas. You see why I don't like S's with 5s? In total, that equals 78. I'm running into this. 50, like that. Boom. The other one is you sold a total of 87 hot dogs and sodas combined. So the number of hot dogs with the number of sodas, H plus S, equals 87. But check it out. This first equation has to do with dollar amounts. The second equation has to do with items, number of items sold. And the units line up with that. Number of, right? Total of hot dogs and sodas here. So all the equations there, they change based on what you have, and you have to make sure that when you define them, it helps you create an equation because you can use these words, this exact string of words, this phrase, in your statement. If I multiply the amount of dollars per hot dog, per each hot dog, times the number of hot dogs sold, blah, blah, blah. So that helps. And then same with this one as well. Now this one's really interesting because going back to the idea of we're not talking about number of, we're talking about cost of. Sometimes when I ask students, say that we write 3 hot dogs and 3 sodas is $11.25. So boom, boom, boom. Hopefully you can agree that that's a proper equation. I'll sometimes ask students this. What does this mean? Most of them say this. 3 hot dogs. H isn't hot dogs. Sorry, I'm going to yell this. H is not hot dogs. H is cost of each hot dog. 3H doesn't mean 3 hot dogs. 3 means 3 hot dogs. H means cost of each hot dog. When I multiply 3 hot dogs by the cost of each hot dog, I get the total amount I spent on all 3 hot dogs, not 3 hot dogs. So it's super important that you know what they mean, and this helps you do it. So not just how can one easily do it, why should we do it? You're starting to make sense of it. I'm going to move on from this question, but hopefully that idea is making sense. And you can tell that I'm very animated about it because no matter what I say to my students, and trust me, some get it, but some, no matter what I say to my students, they still go back to H equals hot dogs. And that's an issue. It really is. There's so many characteristics within hot dogs that we could be identifying. In one case, it was number of. In another case, it could be price of. In another case, it could be length. It could be weight. There are so many different things you can do. And you have to be very, very careful about what you're doing with each one. Okay, so that's it for question number 1. I'm going to go on to question number 2 here. Whoops. What step is done first when solving a literal equation? Now, before you get a little too confused here, a literal equation is an equation that it's like formulas, ones that mostly just use letters, and when you solve for a variable, you're not necessarily getting like an answer, like x equals 3. You might get like x equals a minus y times the quantity m squared and like all that. So what step is first done when solving a literal equation? I'll give you an example of one to give you the idea of what goes first. Let's say you have ax plus by equals c, and then I want you to solve for y. Now, I'm not going to solve the whole thing. We're talking about what step is done first. Maybe the next question I can do this because you'll see it. And I say solve for y. Well, what step is done first? It depends on the question. On this question, solve for y, determine it based on your objective. The objective is to solve for y, so that means get this term by itself. So in order to get it by itself, you might have to move some things over to the other side of the equation. But the whole goal is to make something that says y equals. So in order to do that, you're going to have to take probably multiple steps to get it done here. And for me, generally, it's try and identify where your variable is and figure out ways that you can get it alone, one step at a time. So I would first go for trying to get this term alone, b times y, which means I would move this thing over, right? And you move it over because it's added, you would move it through subtraction. So what first step is done? It depends on what you're solving for. If I solve for a different thing, I'll have a different objective. But it's all about where is your variable? Does it occur more than once? And we're going to see a question on that. Does it occur more than once? What do you have to do to get it on its own side of the equation? But you got to seek the variable out. So what first step is done? Seek your variable and find out then when you can isolate it. So to get it to y equals, again, my first step, I would have subtracted ax from both sides because here, now that's gone and this is all that's left on that side. So it all depends on the problem, and hopefully I can do some other problems to get you through that. but see what you're solving for. It always changes. I could have another formula that says a equals pi r squared, okay, and we say solve for r. Okay, well, two things are happening to r. R is being squared, and r squared is multiplying by pi. So again, when it comes to getting it by itself, there's so much other stuff in the way. Now, this might be asked because there was a different question that was like, I don't know, it was bigger. I don't even know if it was a real, you know, there was. It was kind of for an area of a trapezoid. Like area equals 1/2, and I think they use the letters a plus b. A lot of the questions have questions within, which is interesting, meaning I'm looking at other things that I have to talk about in other questions in the formulas that I'm doing. And there was a question like this, and it said solve for h. Now, in this one here, again, I identify where h is, and I say, what do I have to do to get it alone? And this is important because some students might have looked at this to say, let's distribute the 1/2. Let's distribute the 1/2. And not that there's anything wrong with it, but it's really not suggested. The 1/2 isn't interfering with that h any more when it's factored like this than when it's distributed later. So you should probably just leave it like how it is. It's not interfering. It's one of those things that, you know, when students learn distribution, they say anytime you see it, you probably want to try and do it. That's not necessarily true. I told them this. It's like that Jurassic Park quote with Jeff Goldblum where he says something like, you got so like hell-bent on deciding whether or not you forgot to think about whether or not you should. It had to do with the ethics of like giving birth again to dinosaurs. Because of course, like, you know, whatever. But so again, getting h by itself, why would I distribute first when I can find other ways to move the terms over? And then that kind of leads into my next question. So again, identify what it is you have to do, like what you have to solve for, what's your objective, and then say, how do I get it by itself? And that kind of comes to my next question here. So the third question here is, how do you know when to add, subtract, multiply, or divide when solving a literal equation? Now again, in terms of talking about this, I haven't done the ones with squareds where I had to move, like solving for r, I had to take the square root. So we've only done add, subtract, multiply, divide so far. We've done linear equations, not quadratics. So how do you know when to do one versus the other? Well, point blank, and I'll go back to the ax plus by equals c and solving for y. Solve for y. You do it based on what inverse operation you'll have to do. And by inverse operation, I mean, how are some of these other things affecting y, interfering with y? I'm going to make y a different color. How are some things affecting y here? Let's go ahead and do the opposite of what it's doing to y so that it removes itself from this side of the equation. The first time I said I want to subtract ax from this side because ax minus ax is 0. It makes it go away. Now, how did I know to subtract instead of add or multiply or divide? Because ax is already adding on this side of the equation. Not because this plus, by the way, it's because this plus. You don't see it, but if it's positive, that means it's a plus. Let's put it this way. Let's say this said minus. Let's say this right here said minus. Is ax still adding here? Yes. What if I rewrote this and said negative by was first? Ax is still positive. Whoops, there's just a c. Ax is still positive there. So it's not like it ever became negative. So because it's adding on this side, I'm going to subtract it over. Ax minus ax is 0. And whatever I do to one side, I do to the other. But I know to do that one because I'm doing the inverse of what's affecting y on that side. Now it's gone. And I'm going to leave this as a plus here. But now it's gone. So all that's left is b times that y value, and that equals c minus ax. Keep in mind, those didn't combine or anything. They just stayed there. So now what do I do? Well, b is multiplying with y. B times y is something. So to figure out what y is, take that something, and we actually divide it by b. If I divide it by b here, here and here, b divided by b is 1. And that's our form of cancellation, because to get y by itself, we want 1y kind of plus 0. You know what I mean? So y, I'm just going to box it. So y ends up equaling all that nonsense there. Right? And the point is, we solved two-step equations before, and people were okay with the way that it was written. But suddenly, when they got into letters and such, they got a little confused. Let's say I ask somebody to do 5 plus 2x equals 13, and I asked you to solve for x. A lot of people wouldn't have any trouble saying, let's subtract 5 from both sides, and then you have this, and then let's divide by 2 on both sides. For whatever reason, as long as you get numbers out, you have no problem looking at it. And maybe it's because you don't like not being able to combine like terms, and you don't like having to write it as one big fraction and not being able to get it in something small. And I acknowledge that. It's not like this looks simple to me. It doesn't look simple, but the concept is no different. Look here. I subtracted this from both sides. I divided this from both sides. So as long as you have a way of using these things right here, you should be able to know what to do. Same thing. It doesn't matter if it's a literal equation or a regular one. It's the same thing. Just sometimes terms don't combine. So again, when it comes to that, how do you know what to do? You do the inverse of whatever it's affecting your variable with on that side of the equation. If your variable is dividing x over y equals z, and they say solve for x, if it's dividing by y, you're going to multiply by y. Now, one thing of note that I want to mention, if you're trying to solve for y here, you got to get it in a numerator. You can't just divide both sides by x and say y comes on top. You'd have to multiply both sides by y and get it in the numerator to start, just so you're aware. Sometimes you have to do inverse operations on your own term, on your own, variable you're trying to solve for, because, so x equals like y times z, because you have to get it in a numerator. It needs to say y equals, not 1 over y equals. Okay, so that's the idea for question number 3 again, and that goes to a lot of the literal equation stuff that people might have questions with. So if you're ever really truly confused with it, I would just simply say, try real numbers in its place first and say, what would I do here? And I think that's going to be the best go-to, the best goal for you. Okay, so let's go on to question number 4. And question number 4 is this. How do you solve for a variable placed in two separate terms that can't combine? I'll be honest, I haven't done these with my classes, so the fact that somebody asked this is kind of interesting. I think it showed up in our book. I'm going to go and create a problem and kind of give you the idea of what the heck it is we're even talking about. Let's say we have an equation that says solve for x, and just let's use the ABC scenario. Let's do like ax plus d equals bx plus c. Okay? Now I want you to solve for x. Now, compared to question number 2, when it said what's the first step you do, my first step is identify your objective. We have to get x by itself. So look for your x's. There's an x, and it just so happens there's an x here. So a little interesting. This is the first time you're seeing one where x is in multiple terms. And the thing is, if these were real numbers, 2x plus 3 equals 4x plus 5, whatever, most people would be okay with this because they just say, oh, let's just move the 4x over, and then these combine, and you get negative 2x, and you know what I mean? You're getting x by itself in an easy way. You're able to, because you can combine like terms. But now people look at this and say, well, okay, but what if I tried that scenario here, and I tried to move the x terms to one side of the equation? What if I subtract bx from both sides? And I understand this will look confusing, but what if I subtract bx from both sides and just already I'm going to subtract d from both sides to move the non-x terms over? So boom, boom. I'm gonna have ax minus ax minus bx equals c minus d, which is cool. But how do I get x by itself? How do I solve for this thing if the terms can't combine? And I can't answer this question easily for my students because we haven't done this next step, but I want you as a student of mine to consider what you really do when you have like that 2x minus 4x. What are we really doing? One way that you can say it, just so I don't overspeak about it, is you keep the variable and you subtract the numbers. And one way, and because remember, this is multiplication, 2 times 4 times. So to keep the numbers here, one easy way of writing it is like that, 2 minus 4. 2 minus 4 gives you negative 2, and negative 2 times x is negative 2x. So instead of writing all those steps, though, we just do 2x minus 4x, and it combines and makes that. But think about what we do here. You keep the variable, and you subtract the coefficients like this. Check this out. A minus b, if I write that in the parentheses in the quantity and subtract them and I multiply by that coefficient, that gives me the same setup as this right here if you bridge that connection. Now what I truly did, for those who are in higher algebra stuff, what I truly did is something called factoring. It's the opposite of distribution. It's the opposite of distributing. So take a look at this. If you distribute the x back in, does that give you this? X times a is ax and x times negative b is negative bx? Yeah, so you factor an x out of there, and what's left inside is a minus b. So really the answer to this is by factoring. You clump all of your x terms together, the ones that can't combine, if they're all x to the first power. You factor x out of there, and now suddenly what you have here, take a look in this equation. I'm excited about this. Now suddenly what you have is a product of this quantity. And I need to get this by itself. So obviously I'm not going to distribute. I just factored. I just came from there. But I have a product. If something's multiplying by my variable, I divide both sides by it here. A minus b, and these can go away for the same thing. And so that's your answer. X equals c minus d over a minus b, and I'm set in stone. I actually solved for x and things that couldn't combine. And it came through factoring. I did it by factoring. And again, that's a term that I'm not going to do too much factoring with my class, actually. We're going to do first semester based algebra stuff. Not a lot of factoring is going to be involved. But that's how you would do it. It's possible to do, and that's how you would do it. Okay, so there goes that question. I liked the intrinsic value behind it and someone exploring a little more because they didn't really get to see too much of it in my class. Okay, so the next question I want to answer here is question number 5. Why do we use capital and lowercase letters as different variables? So I just I was mentioning before that I was doing questions that kind of reminded me of this stuff. I wrote down ax plus by equals c. Notice how the a, b, and c were capital and x and y were lowercase. I also had area of a trapezoid. I wrote it like this. Okay. Notice there's a capital A and a lowercase a right here. Now this one alone can actually kind of answer your question within itself. Why do we use them? One part is so that you can make sure that you differentiate them as two different variables. Capital A and lowercase a are by no means the same variable, and by no means do they have to associate with each other in any sort of way any more than, say, A and B associate. A and B are actually closer to each other for this. This is area of a trapezoid, and a trapezoid is designed, I probably had a trapezoid tool, but a trapezoid's area is found by averaging your bases, taking half of the sum of one base and another base, and multiplying it by your height. So that's the total area. So this is a base length, lowercase a, and lowercase b is another base length. So these two have a lot more to do with each other than that capital A has to do with the lowercase a, because this is area and this is base length. So one reason we do it is to make sure that we can differentiate two different things that occur in a formula. Now base doesn't start with a, and you actually normally don't see the formula for this one have a, and I'll show you a different way that you can write it. Two different ways actually. One of them is by doing 1/2 capital B plus lowercase b. Now, I don't recommend this actually for a couple other reasons I'll talk about for capital and lowercase letters. But you could also write it this way, where capital B and lowercase b have a lot more to do with each other this time than capital B and capital A. So you can see there are discrepancies. But again, I wouldn't recommend this specific one because of how we universally tend to use capital letters. And that's going to be another question in a bit. Now, another one that actually does, this is for area of a regular polygon. Area equals 1/2 apothem times perimeter. In this case, A stands for area and A stands for apothem. So, you want to use two different variables, and we can uppercase and lowercase one. Now, this one here is a little different story within itself because these involve coefficients and constants. So there, I could make a bullet point list, and unfortunately I'm not going to. I'm just going to talk through it. But there are a bunch of different reasons for which you might actually just have variables, lowercase and uppercase. And one of them is if you have constants of some sort. Constants and coefficients will sometimes be used as uppercase, so your variables, you know, the non-parameter values, the ones that can change and you can solve for, will actually be represented as lowercase. That might be one reason. A second reason, and you kind of see them with the apothem and perimeter ones right here, or the area ones right here. All the ones that I've talked about right here, these capital letters for A, that was area. And these other ones, apothem and perimeter, base length, and height length, these are all lengths. These are one-dimensional units, and these ones were areas. You might have seen this before. I wrote A equals pi r squared earlier. Pi is a Greek letter constant, and it's a lowercase letter that represents a number. R here is a variable that is based on variable for this and this and that. But R is a length, A is an area. Okay. Now, one exception, circumference equals 2 pi r. Sometimes I use a capital C. I don't know if you actually should be or not. But that's there. But volume of something like pi r squared times height, that's the volume of a cylinder. Volume is also capital letters. So generally, you'll see capital letters when you use area and volume, but you'll use lowercase letters for lengths. So one-dimensional units, you'll generally use lowercase. Two-dimensional and three-dimensional units, you'll actually start to use capital letters for that. And you're going to see that more often than not. It's kind of a universal code. Is it required? No. But if you're going to use A for two different variables in a problem like this one, you can't use lowercase for both of them. Furthermore, if you start with one as lowercase, you can't suddenly change it later to uppercase. And same with this one right here. And it doesn't matter if there's another A there or not. If I do A equals pi r squared and later I find out the area is 30, whatever, I can't just call it lowercase a suddenly. You stick consistent with whatever you had. If it was uppercase, keep it as uppercase. And so, you know, that's important when we talked about things like S, because S looks like a 5, or like L, a lowercase l can look like a 1, so you should curve it. A lowercase e can look like a plus, or cursive it here. You should curve this here. A z can look like a 2, depending on how you write it. So you should, you know, put a little cross thing through it. An O like a 0. So there are a lot of different things that, you know, if you're going to do lowercase, just be careful. Because some people say, if you can't write lowercase, then make it uppercase. Or, you know, whatever. I wouldn't do uppercase 2 or Z or O. So if you know what I mean. Other reasons. If you start learning geometry stuff, if you're talking about like a triangle, in a triangle, you might have the vertices, points in planes and points as vertices and stuff, you will generally see as uppercase. Likewise, the lengths that are the sides that are opposite them, those lengths will be deferred to as lowercase. So I can know that the lowercase a corresponds with this uppercase a because it's opposite its angle. So the lowercase ones will be side lengths, the uppercase ones will be for angle measures, and for planes, and for points on a line, and different things like that. In calculus, you'll use a lowercase 1 to do something for function, but then the uppercase one, like lowercase like f of x, will be for function. Uppercase f of x will be for its integral. There are different ways and reasons that we've done them in math. Hang on, I have to go back to my screen. There are different ways and reasons that we've done them in math in the past that are still used today. And the general things that you just have to note are whether or not you want to choose to follow it, at least now you can make sense of it, that people had them for different reasons. Is it required? No. But if there are two variables for the same letter, there are ways around it. One make uppercase, one make lowercase. And here's another way. I said I was going to do this with the trapezoid thing right here. In a trapezoid, they actually normally don't use A or B. They actually use B twice, and not both, one uppercase, one lowercase. They'll use two different B's. Let's say I want to do a lot of different B's for something. I could do B sub 1 and B sub 2. I can write little subscripts there and say this is for one base and this is for another base. And I think you'll generally see that formula for area of a trapezoid look like that. So it's going to be b sub 1 and b sub 2 like that. This is really important if you're doing something like coordinate pairs. Let's say on a coordinate graph, you had this xy value, and you had this xy value, and you had this xy value. Suddenly you have so many that you can't call them all xy because x has to represent one thing and so does y. So we call this x1 y1 and x2 y2 and x3 y3, and it kind of just helps you denote the fact that they all represent the same thing. Those are all x's, but they're going to be different x's and different y's. So why do we use them? There's a universal language and code behind it, and for logic and convention, we have to make sure we separate some things with others. Not always required, but we do. So keep in mind, if you're going to solve something that had like I think we had something, an equation where there was an uppercase and lowercase c solving for some w. It was 1,000 capital C over lowercase t times lowercase c. These c's cannot cancel out and divide because one is uppercase, one is lowercase. They don't mean the same thing. So just all those things are very important to note. Why do we use them? Again, to distinguish one thing from another, especially when they spell out the same, when they stand for the same, when they start with the same letter. And then they were used for different purposes, for geometry, as you saw, for volume and area and things like that. So that's kind of where it comes from. Okay. So there's that question. I know I'm running way past any time I'd ever want to do. So I have one more question for you. And the final question for you, which I promise to kind of cut short if I can. What jobs do people actually use? What jobs do people, I probably wrote it wrong, but what jobs do people actually use variables? There we go. That makes sense. What is the use for them in real life? All right. Use for variables in real life, like I can't answer that very well because we use variables without using them. Variables are just a substitute for something we don't know. If I said what's 2 plus 2, I could also write that as 2 plus 2 equals x. I used a variable. It represented an unknown. Or 2 times what equals 6. That's 2x equals 6. I don't have to say a letter in place of it to make it a variable. If someone says, oh, let's see, what time do you want to go to the game? Like, well, let's see, it's 5:40 now and we want to leave in about a half hour. So, 6:10. Like, right? Like, you're using the idea of variables without knowing it. Just, I want you to understand that. Now, we don't have to say x for those things, but equations become so much more complicated, or numbers are so less obvious that it's easier to construct it in a way that this algebraic inverse operations and factoring and stuff actually helps you more than it hurts you when it comes to solving. Now, the other portion of this that you want to ask is, what jobs do people actually use variables? And your question can come in many forms. One of your questions can end up being, which jobs do we actually have to solve for x in? Okay, if it's that question, I'll be honest, there aren't a lot. Math teachers is one of them. Being a mathematician or some sort of engineer or a financial accountant or a nuclear engineer or a computer scientist, and I'll talk about that more, programming. Or heck, even if you are a baker, like bakers will use them for special ingredients when it comes to nutritional amounts of things. They want to be able to optimize their stuff. There are ways that you solve for variables to determine things. I used it for my fantasy baseball league when it came to figuring out what ERA, how many earned runs can I give up and still lead the ERA category in my thing to beat my opponent. I literally wrote out an equation to make it happen, and it worked. But so how many actually use variables that you solve for and you have to handwrite things and stuff? Not too many. Okay, not too many. If this is more about literal equations, all the variables that we talked about, you can always use them to isolate a variable in a different way to find a different thing you're solving for. And I'm not going to give a bunch of examples with it, but I'll give you a particular one that's actually useful for your math class that you'll be thankful for later. If you start taking second semester algebra, you're going to learn what are called quadratic equations. And a quadratic equation in a general form is one that might look like this. Something where you have a quadratic term, a linear term, and a constant term that can't combine or do anything like that. And there are a lot of times you have to solve for x, like when they have actual numbers, 2x plus 5 2x squared plus 5x minus 6 equals 0. Something like that. Solve for x. What x value makes this true? Now, there's this thing called the quadratic formula. That's this nice way of getting x by itself. And I'm not going to do it for you, and it wouldn't make sense to my students. But the formula looks like this. And I know you might be perplexed by it now, but anyone who's used it over time says, I love it, because it's a nice foolproof way of me being able to solve my equations without having to do a lot of picky stuff here. Okay, now there's a way to get x by itself here that involves inverse operations. It involves completing the square. It involves using common denominators. There are a lot of different things that you do with it to get it by itself, but you should thank whoever first came up with being able to get this by itself to make it happen. And that's going to lead me into my next thing here. Your phone, my computer and camera that I'm recording this stuff on, your TV, any technology that you have, bridges, be thankful that somebody knew algebra to make that. Cars, be thankful that someone knew algebra to at least get something started to make that happen. All right? Have respect for the idea of the profession. Even if you don't end up doing it, doesn't mean it's not useful in your life. So when you ask what is the use for them in real life, you're looking at it, baby, because you're watching a screen where algebra had to be used to make every bit of technology happen, because it's all about optimization, and that goes back to the idea of programming. I'm a computer science major, and as a computer scientist, I have to speak for myself in saying that almost literally everything that you do is variable based. You create a variable, and it's not always that you're solving for something, and that's the thing that I think that we have to make sure that we're making sense of. You're not always solving for variables. Sometimes you're having, if you ever used Excel and you had it create formulas and spit out numbers, those variables are used for those sheet things, but you're keeping something consistent to make something go very fast. In one of my math classes, we had to design we used something called a hailstone sequence. And instead of computing numbers bits at a time, I said, I can do this in a minute. And in 40 seconds, I created something that I could create a hailstone sequence for any number in the world. And you don't know what that sequence is, but the point is it spit it out immediately. And you don't have to do anything by hand, anything by calculator. Excel did it for me. So as a programmer, you have to have appreciation. Variables are often used for modeling things and for inputting values from something to make something happen. And we're going to use a lot of modeling things later. You might use something to model a profit scenario to say what price point should you, as a business, what price point should you set something at to yield maximum profits. You set the price point too high, people aren't going to buy it enough. Set it too low, you're not going to make enough money off of it. There's an equilibrium. It has to do with quadratic modeling. Sinusoidal functions for tidal waves, for tide seasons, and trying to figure out when's high tide, when's low tide for things. Models are used everywhere. Geographical, climate, meteorological, weather, everywhere. And not going to sit around and talk about all of them. I promised I wouldn't, but you're not always, number one, you're not always solving for something. And number two, oftentimes you're going to let a calculator or computer do it for you. So keep in mind when you're doing these things, it's to help you sustain and make sense of algorithms. And it helps build into future math classes where you got to do certain things. It's not always about, and that's the important thing. I'm going to go back to question number 1. Remember what I mentioned back here with these word problems. I said I didn't even have my students solve the thing. I didn't even give them the question. I'm going to go ahead and hide these questions right here as well. The how many, whatever, who cares? That wasn't the question. Sometimes it's not about answering a question. Sometimes it's about how can you decode and deconstruct a problem and break down what's happening and make the most sense out of it so you can develop algorithms. You don't get to be a computer science major, or you don't get to get in the computer science profession without having a certain mind that is innovative enough to design algorithms to make sense of things and to be able to debug and decode. I'm speaking beyond what I need to, but it's useful. I promise to you, it is extremely useful. Not only that, even if you never use it again, your mind has grown in some way that it will be useful for something else. So when are you going to use it in real life? Point blank, always. You might not know it, but always. That's all I got to say. All right, so that's it for this one. A nice, big, resounding, long 45-minute one for you guys. Thanks for watching if you did. These things I always find a way to make this shorter. I promise someday I'm going to make this 15 minutes long or something like that. But not today. I'm going to go ahead and kill this one off, though. My name is Mr. Robinson. Take care.